So today's topic of discussion is about an HPLC column. That is going to be about how to determine the HPLC column's volume and how to understand the porosity of an HPLC column. Hi, my name is Bhaskar Napte. I am the founder of Pharma Growth Hub, and I am on the mission to provide an absolute clarity on such a very important topic to the pharmaceutical professionals. So in case if you want to understand the services provided by the Pharma Growth Hub, please find the details given in the description below. So let us understand from the question why one has to measure the internal volume of an LC column. So these are the important points. Once you understand the column volume of the volume of an HPLC column, you will be able to determine how much long it's going to take me to equilibrate my column during or before the analysis. You will understand how to equilibrate my gradient programs, how long it is going to take me to equilibrate my gradient programs. You will also able to understand what is the column hold volume, what is the load the column can take in terms of injection volume, and of course at the end you will also able to understand how much time I need to take to clean my column, that is the column washing. So these are the four important points one has to consider based on to an HPLC column's volume. So before we discuss about column volume, let us also understand something called as the HPLC column porosity, because this term needs to be understood if you really want to understand the exact HPLC column volume. Without understanding the column porosity, one cannot define the exact column volume. So what is the column porosity? And here is the definition of that. The column porosity refers to the measure of the empty space. What it is empty space within the column packaging material. Suppose you have this column in the place now. This is the column, for example. I'm so sorry for this bad structure. Okay. But in this column, all this, though the column has the packaging material, I mean, it's your stationary phase, but do you think that the 100% volume will get occupied by the stationary phase? Absolutely no. And there is going to be the empty space available. Oh, here is small empty space, here is small empty space. And we'll talk about how one can determine this empty space or the column porosity. So there are two types of porosity to consider in HPLC column. The first one is the porosity because of the pore size. We know that especially the column is made up of the maybe a stationary phase support like an silica, and this silica comes with a certain particle size, and that particle size has certain pore size, maybe 70 angstrom or 100 angstrom. So how this pore size is going to contribute to our column's porosity? So this refers to the size of the pores within the individual particles of the column packing material. So we talked about, yes, our stationary phase comes with the particle, and this is the, let us say, spherical particle. And on this spherical particle, maybe a 4.5 micron, you will have a small pores. Let me denote it by the blue color. Now these are the 70 angstrom or maybe 100 angstrom size pores, isn't it? Now does these pores empty, hollow, or what are they? They are actually the hollow spheres. What they are? They are actually the empty spheres. And hence if they are empty, then they can certainly contribute to the column porosity, because column porosity talks about the empty space within the column. I hope you understand that the first important aspect is understanding the pore size of the column, and that can certainly contribute to the column's porosity. Let us understand the second term that can define the column's porosity, that is called as the particle porosity or interstitial porosity. What is the definition of it? Now this is the space between the particles of the packing material. Suppose you have the two particles of 4 micron, isn't it? This is the second particle, and let me draw the third particle also. Let us have the particle this way. Or can I draw the particles with little low, I mean smaller shape for explaining better? Let us understand now. Can I erase this? Okay, I can erase it also. Let us draw the particles once again. So this is one particle, this is another particle, isn't it? And this is the third particle. This is the third particle. This is the fourth particle, right? Okay. Now can you see there is some space available between this particle, this space, isn't it? And this is called as a interstitial porosity because of the space between the particles of the packaging material. So this is the first one, or rather, this is the second one we talked. This is contributes to the or this become the reason for the column's porosity, and we also talked about the pores present inside the particles, right? Let me draw by blue color, right? So this pore size also adds to the spore size. The spores present onto the silica particle, your stationary phase, can also contribute to what? The porosity of the column. So I hope you understand that two important factors needs to be considered while defining the column's porosity. So the column's porosity is nothing but the empty space within the column. So it should be noted that different packing materials will have significantly different porosity. For example, you have the fully porous particles versus core shell. So especially core shells are quite tightly packed columns, and the fully porous particles are not that tightly packed, and the fully porous particle may have the more porosity as compared to the core shell columns. So for example, more porosity means what? More empty space. Understand this point. More porosity means what? More empty space. So is it good to have the more empty space? No, isn't it? But also understand that if you have the complete tight columns, what about the column's back pressure? So your mobile phase should also able to flow through the column, isn't it? So that balance has to be achieved. So it is not that okay, something if you have the very tightly packed column, it is always good. You may have the challenges. And for such a columns, you may need to go for an UPLC. So for example, A's fully porous particles have porosity of 0.63, while A's ultra core, means core shell particles have a porosity of 0.55. Now the important question is how you can able to calculate this column volume. Which we started with understanding the column, first start with understanding the calculation of the column volume, and then we'll also understand how one can calculate the column porosity also. So what is the volume of any cylinder like a steel column? It's a cylinder, right? And it is denoted by this formula pi r square L. What is the R? R is nothing but the radius and L is the length of the cylinder. If you substitute this R by diameter, the diameter is, the radius is half of the diameter. So this dc by 2 stands for radius. And again, this is the square of the whole term. So you can also calculate the volume of the steel column by this calculation formula also. This is the another calculation formula. And especially in case of an HPLC column, we don't talk about radius, but we always talk about the diameter. So that's the reason I consider this particular conversion from radius to diameter. Okay, let us move on to understanding the importance of the porosity now. However, as the column is packed with packaging material, only a fraction of the column volume is available to occupied by the mobile phase. Means what? Your column has lot many empty spaces. We talked about those empty spaces, isn't it? So it is not that the complete column volume is available for mobile phase to get occupied. It's a very small amount of volume will be available for mobile phase inside the column. Now multiplying by the column porosity or empty spaces within the column packing materials provides an accurate value of VM, and VM stand for the column volume which is available for mobile phase to get occupied. So you need to multiply by column porosity. This is the calculation formula which is more practical in case of an HPLC column containing the stationary phase. You can see over here, this is the same calculation formula by the way, completely almost until this point, isn't it? Just compare these calculation formulas. These are the same calculation formulas, but only change you will find this porosity has got multiplied over here. And this is going to help us to understand what is the space of the column available to get occupied by the mobile phase. And this is the only space which can get occupied by the mobile phase. So multiplying by the empty space is going to help you to give the practical available empty space within the column. This is stand for the column internal diameter in mm. L is column length in mm. Epsilon is column porosity, and R stand for DC by 2. Okay, please forget about this 2 of a square. This is a typo error. I hope you understand this. Okay, let us move on to the fully porous particles have porosity of between zero point 0.6 to zero point 0.7. And we also talked about the core shell columns, especially in case of the what do you call, what is the example we took by the way? I think we talked about example of S column, isn't it? It was having the porosity of 0.55, right? So the core shell columns has the less porosity, and the core shell has the less porosity, but the fully porous particle has the more porosity. So let us understand how one can determine the column's volume and the porosity by conducting very simple experiments. By conducting the very simple experiment. So this is the example I would like to give you to calculate the column's volume now. So both VM stand for the column volume, epsilon stand for the column porosity, can be determined by measuring the column dead time, that is a T0, by injecting the unretained analyte or just simply by injecting the mobile phase. So what you can consider in case of, if you want to use the unretained analyte, you can think about an uracil in case of RPLC or thiourea, or you can also use the toluene in case of the Hillick mode operations. So in case if you inject the unretained analyte or just the mobile phase, you will see that your T0 is 1.618. Just this is an example for explaining this particular calculation. The flow rate was 1.1 ml per minute, and the column is 150 mm, 4.6 mm, 5 micrometer. So calculating the column volume. So this is the calculation of the column volume. T0 into F. What is the T0? It's the column's dead time in minute, and flow rate is in terms of ml per minute. So in this particular example, understand our T0 is 1.618 minute, and our flow rate is 1 ml per minute. So what gets happen in this case now? Usually understand that this minute get cancelled out this minute, and you will actually get the volume in terms of ml, that is nothing but the 1.618 ml. I hope you understand. This is our column volume. I mean, this volume can be occupied by the mobile phase. This volume can be the interspaces between the particle size of the stationary phase, or the pore size, or the pores volume of the pores present onto the particle size. I hope you understand how it has calculated. Now, how can I understand the porosity now? Here is the calculation. So if you rearrange the calculation formula that you have seen over here, okay, let me take you back. And I have considered this calculation formula, where it is this calculation formula. Vm is equal to pi and entire this. So you can calculate the epsilon is nothing but the porosity by taking these all different terms onto the left side. I hope you understand the rearrangement of the calculation formula. Let us now come to the same page where we are going to talk on calculating the porosity now. So this is the rearrangement, and this is the epsilon Vm divided by this entire factor. So how much is the value we have for the Vm now? This is 1.816. We just calculated. Pi is 3.14, isn't it? This is diameter of the column is 4.16. Look at here, 4.16 mm. And L is the length, that is the 150 mm. It is a 150 mm. Right. So if you substitute all these figures now in the above calculation formula, this is a very interesting point to be understood. This conversion now. See what I did now. This 1.618 ml can be written as a centimeter cube, if I am not wrong. 1 centimeter by 1 centimeter by 1 centimeter, that gives me a 1 ml. So this is the same unit, but expressed in terms of centimeter cube. Centimeter cube. I hope you are clear on this point. 1 centimeter cube is equal to 1 mm. All right. Now what I did, I converted this mm into a centimeter, and there is a reason for that. I will talk about that very soon. So that will become 4.6 mm is equal to 0.46 centimeter, right? So this is 0.46 centimeter. And similarly, I also converted this 150 mm into centimeter, that is going to become 15 centimeter. See what I did? I tried to make the same unit for my numerator and denominator. Numerator and denominator. So now what is this now? This also becomes centimeter square. Understand this square part. So this becomes centimeter square into centimeter becomes what? It actually ends up getting the centimeter cube. I hope you are understanding what is the purpose of making in the same unit. So this centimeter cube, right, which is getting cancelled by this centimeter cube, right? So at the end, this particular unit, this particular term, porosity is going to be an unitless term. Hmm? So converting into the same unit is very important. So then you can calculate and it will be 0.649. 0.649 is the porosity of this particular column, isn't it? So this is the space available for mobile phase to get retained. Mobile phase to get retained. Now moving ahead, now when I inject this particular uracil or unretained just a mobile phase, this particular T0, will also get because of the some additional extra column volume. It is not only because of the column volume present inside the column, but this T0 can also be because of the extra column volume. So I'm going to introduce the new term to you, that is called as the extra column volume or ECV. So what is the ECV, by the way? So when measuring the column volume via determination of T0, you are actually measuring the column volume plus extra column volume. Because of what? Because of the internal column volume, because that is the internal volume of the flow path within the system from injection until detection. And what are those extra spaces which are going to occupy the volume? Maybe anti-sampler components, your injection components, your tubing which is connected injector to the column to the detector, your detector flow cell. Now all these are the extra column volumes. They are not the volumes occupied by the column, but they are the volumes occupied by another components of your HPLC system, like needle seat, valve, tubing, and flow cell. So calculating the extra column volume now is important. So disconnect the column from the system, remove the column, and you can connect the union. Especially union should be a zero dead volume component. Union should not carry any volume itself. So once you connect this union, you can inject just an unretained component like uracil and calculate something called as the time delay between injection and the start of the peak, that is a T delay. So in the given example, we have calculated the this particular time delay, which is found to be zero point 0.4 minute, and this is start of the peak. This is just the start of the peak. So this is 0.4 minute. So what is going to be the calculation formula for extra column volume? It is going to be flow rate into T delay, and flow rate is in terms of ml per minute. So if my flow rate is 1 ml per minute, now if you can look here now, right, the flow rate is 1 ml per minute, and my delay time is zero point 0.4. So 1 ml per minute into 0.4 minute. So this minutes gets cancelled, and I will have zero point 0.4 ml as my extra column volume. So once I understand the extra column volume, let us now understand how to calculate the exact column volume. Because in my calculated extra column volume, this zero point 0.4 ml is not from the column. It is coming from the extra column volume component, and that has to be subtracted. So if you remember the calculation of the column volume, this was the earlier calculation formula, P0 into F. But now I am going to subtract this extra column volume from this calculation. And if I know all the figures, my earlier calculation was with 1.618. This is T0, 1 ml per minute is the flow rate. I am going to subtract the extra column volume, and 1.6 minus 0.4, I will get exact column volume is 1.218 ml. Also, I need to consider calculating the exact column porosity. Now, this is my old calculation. I got this is the formula, you know, right, for a porosity. Now, this is my new exact column volume, 1.218 ml, right? So, if I substitute the new values now, I will get the exact porosity as 0.489. So I hope you understand calculating the HPLC column volume and the column's porosity by conducting some very simple experiments. And please don't hesitate to put your question into the comment box below. I will try to answer all of your questions. Thank you so much.